Bismillah ar-Rahman ar-Rahim. Matrix H is a square or skinny. It is of size m by n, m greater than or equal to n. The columns of H are linearly independent. The rank of H is n. The rank of H Hermitian H is n. H is a random matrix. The components of H are random variables. Specifically, they are independent and identically distributed, zero mean, unit variance, circularly symmetric Gaussian random variables. The objective here is to obtain the expected value of the natural logarithm of the determinant of H Hermitian H. Let Hk be the kth column of matrix H. Let H with subscript minus k be matrix H without the kth column. So H minus k is a matrix of size m by n minus 1. We can write matrix H as the first column, H1, and the remaining columns, H minus 1. So this is the matrix starting from the second column of H all the way to the nth column. Let's write down H Hermitian H using this partitioning. H Hermitian is H1 Hermitian, H minus 1 Hermitian. Here is H. Multiplying, we get an n by n square matrix. Here we have the scalar H1 Hermitian H1. Here we have the n minus 1 by n minus 1 square matrix H minus 1 Hermitian H minus 1. We also have H1 Hermitian H minus 1 and H minus 1 Hermitian H1. If we have a matrix with 4 blocks, A, B, C, and D, this block is a square and of size k by k. That block is a square with size v by v. The determinant of the matrix of size k plus v by k plus v is equal to the determinant of D multiplied by the determinant of the Schur's complement of D. This is A minus B times the inverse of D, assuming of course that D is invertible, times C. Let's make use of this result in our task. The determinant of H Hermitian H is equal to the determinant of H minus 1 Hermitian H minus 1 times the determinant of H1 Hermitian H1 minus H1 Hermitian H minus 1, then the inverse of this matrix, then H minus 1 Hermitian H1. This is a scalar, a 1 by 1 matrix, so we can actually move the determinant. On the left, we take H1 Hermitian as a common factor. On the right, we take H1. Here we have identity of size m by m minus H minus 1, H minus 1 Hermitian, H minus 1 inverse H minus 1 Hermitian. This scalar is multiplied by the determinant of H minus 1 Hermitian H minus 1 to give the determinant of H Hermitian H. What is the distribution of this quadratic form? It's a quadratic form involving a zero mean Gaussian vector and a matrix here, which is an orthogonal projector. It's a matrix that is idempotent. Its square is equal to itself. The matrix is Hermitian. Its Hermitian is equal to itself. It projects m-dimensional vectors onto the subspace that is orthogonal to the range or column space of matrix H minus 1. If we have column vector X with m components and a projection matrix P of size m by m, if the components of X are distributed like the components of H1, the quadratic form X Hermitian Px is 1/2 times a chi-squared random variable with a number of degrees of freedom that is equal to 2 times the rank of the orthogonal projector. This is when matrix B is deterministic. The orthogonal projection matrix here is random. So given H minus 1, this quadratic form is 1/2 times a chi-squared random variable with a number of degrees of freedom equal to 2 times the rank of this projection matrix, which is m minus the number of columns of H minus 1, that's n minus 1. Despite the fact that we are conditioning on the elements of matrix H minus 1, the conditional distribution of the quadratic form depends only on the sizes m and n, and not on any element in H minus 1. This means that the unconditional distribution of this quadratic form is also the distribution of 1/2 a chi-squared random variable with 2 between brackets m minus n plus 1 degrees of freedom. If this quadratic form is alpha, then the unconditional distribution of alpha is the integral of f of alpha given H minus 1 multiplied by the joint BDF of the elements of H minus 1. And we integrate with respect to these elements. Specifically, we integrate with respect to the real and imaginary parts of the random variables of H minus 1. However, this BDF here is alpha to the m minus n, e to the minus alpha over m minus n factorial. We can take this part outside the integral. The integral is 1, and as we can see, the unconditional distribution of the quadratic form is exactly the conditional distribution. It is also important to keep in mind that this quadratic form is independent of H minus 1. This implies that the determinant of H Hermitian H, here we are using the full matrix H, is equal to the determinant of H minus 1 Hermitian H minus 1. H minus 1 is matrix H without the first column. This determinant is multiplied by quadratic form that is independent of this determinant, because the quadratic form is independent of H minus 1. We know the distribution of this quadratic form. We can write that the determinant of H Hermitian H is equal to the determinant of H minus 1 Hermitian H minus 1 times 1/2 a chi-squared random variable with 2 between brackets m minus n plus 1 degrees of freedom. This random variable is independent of H minus 1. What we can do now is to apply to the matrix H minus 1 what we have done to the matrix H itself. In terms of the columns of matrix H minus 1 is H2, H3, all the way to Hn. We can partition H minus 1 into its first column, which is the second column of H, and then the remaining columns, we can proceed following what we did to matrix H. The only difference is that matrix H minus 1 has n minus 1 rather than n columns. If G is the matrix containing these columns, so it is an m by n minus 2 matrix, then this determinant of H Hermitian H can be written as the determinant of G Hermitian G multiplied by a random variable that is 1/2 a chi-squared random variable with a number of degrees of freedom equal to 2 times between brackets m minus between brackets n minus 2. We also have this random variable from the first step. This random variable is independent of this one. It is also independent of matrix G. Repeating this procedure, we obtain that the determinant of H Hermitian H is a product k from 1 to n, the number of columns of H. We multiply here random variables that are 1/2 times chi-squared random variables. The number of degrees of freedom is 2 times m minus between brackets n minus k. When we take the logarithm, we get a sum of logarithms on the right-hand side. Before proceeding, let's make a digression to see one context in which this quantity appears. Suppose that we are studying the instantaneous capacity of a MIMO system. This is given by the logarithm of the determinant of I n by n plus SNR over n. Here n will be the number of transmit antennas. SNR is the average signal-to-noise ratio per receive antenna. Then we have H Hermitian H. The assumption here is that the transmit covariance matrix is identity. The determinant of this matrix is the product of the eigenvalues. We can write the instantaneous capacity as summation k from 1 to n log 1 plus SNR over small n lambda k. This is the kth eigenvalue of H Hermitian H. If eta is a positive real number, then log 1 plus eta minus log eta is less than or equal to 1 over eta and is greater than or equal to 1 over 1 plus eta. If eta is very large, the difference between log 1 plus eta and log eta gets smaller and tends to 0 as eta tends to infinity. This means that if we have a high average signal-to-noise ratio scenario, we can approximate the capacity as summation k from 1 to n log SNR over n lambda k. We can write this logarithm as log SNR over n plus log lambda k. Applying the sum, we get n log SNR over n plus summation k from 1 to n log lambda k. This is the logarithm of the product k from 1 to n of lambda k. This is the product of the eigenvalues of matrix H Hermitian H. This product here is the determinant of H Hermitian H. The quantity of interest that we have here and its expected value are relevant to the study of wireless communication systems with multiple antennas in the high average signal-to-noise ratio regime. Typically, when we study these quantities, we are interested in averages. So what is the first moment of log determinant H Hermitian H? By the linearity of expectation, the expected value of log determinant H Hermitian H is summation k from 1 to n, the expected value of the logarithms of these random variables. This expected value is integral small x from 0 to infinity log x times the PDF of 1/2 xk. The PDF of this random variable is x to the power m minus n plus k minus 1 e to the minus x over m minus n plus k minus 1 factorial. Consider a non-negative integer L. Let's study I sub L when L is greater than or equal to 1. This is an integral defined as 1 over the factorial of L times integral x from 0 to infinity x to the L e to the minus x log x. Integral IL is equal to minus 1 over L factorial integral x from 0 to infinity x to the L log x d e to the minus x. If we multiply e to the minus x by x to the L log x and take the limits as x tends to infinity or to 0 from above, we get zeros. This can be checked using L'Hopital's rule or any other technique. So when we do integration by parts, we get 1 over L factorial integral x from 0 to infinity e to the minus x. Then we need to differentiate this product here. We get L x to the L minus 1 log x plus x to the L over x. This is equal to L divided by L factorial. That's 1 over L minus 1 factorial. Integral x from 0 to infinity x to the L minus 1 e to the minus x log x. Note that this is I of L minus 1. We have another integral. The outside factor is 1 over L factorial. Then we have integral x from 0 to infinity x to the L minus 1 e to the minus x. This integral is gamma of L, which is L minus 1 factorial. This part here is equal to 1 over L. We have the recursion IL equal to IL minus 1 plus 1 over L. I1 is equal to I0 plus 1 over 1. I2 is equal to I0 plus 1 over 1 plus 1 over 2. I3 is equal to I0 plus 1 over 1 plus 1 over 2 plus 1 over 3. IL is equal to I0 plus HL. This is the nth harmonic number, which is the sum g from 1 to L of 1 over g. To finish this part, we need the integral x from 0 to infinity, e to the minus x log x. This integral is equal to minus a small gamma, Euler-Mascheroni constant. The expected value of the logarithm of determinant of h Hermitian h is equal to summation k from 1 to n minus a small gamma plus h m minus n plus k minus 1. This is the power we have here. The expected value is equal to minus a small gamma times n plus summation k from 1 to n, harmonic number h of m minus n plus k minus 1. If m is equal to n, this summation is h of 0, which is 0, plus h of 1, all the way to h of n minus 1. The expected value is equal to minus a small gamma times n, plus summation k from 1 to n minus 1, hk, which is summation j from 1 to k, 1 over j. Interchanging the order of summation, this is equal to minus a small gamma times n plus summation j from 1 to n minus 1, 1 over j. Then k from j, j is less than or equal to k, so k is j or more. Specifically, k is from j to n minus 1. This sum is equal to n minus j. The expected value is minus a small gamma n plus summation j from 1 to n minus 1, n minus j over j, that's n over j minus 1. This is minus a small gamma n plus n times the harmonic number h n minus 1 minus between brackets n minus 1. Hn minus 1 is equal to hn, the nth harmonic number, minus the nth term, which is 1 over n. When we multiply this by n and simplify, we get that the expected value when h is a square matrix is minus a small gamma times n plus n between brackets hn minus 1. If h is skinny, the expected value of the logarithm of the determinant of h Hermitian h is minus a small gamma times n plus summation k from 1 to n. The harmonic number is summation j from 1 to m minus n plus k minus 1 of 1 over j. We also interchange the order of summation. The maximum value of k is n, so the maximum value of j is m minus 1. What about index k? From here we have that j is less than or equal to m minus n plus k minus 1. So k is greater than or equal to j plus 1 minus m plus n. K must also be greater than or equal to 1. So k starts from the maximum of 1 and j plus 1 minus m plus n all the way to n. If this maximum is 1, we have n terms in the sum. Otherwise, we have less terms. The maximum is 1 if j plus 1 minus m plus n is less than or equal to 1, which means that j is less than or equal to m minus n. So we can take the expected value and write it as minus small gamma n. Then we split the sum with respect to j. J from 1 to m minus n. In this case, this summation is equal to n. Then we have j from m minus n plus 1 to m minus 1. And in this case, the sum is from j plus 1 minus m plus n to n. The number of terms is m minus j, which is n minus this quantity plus 1. This is minus gamma n plus n h m minus n plus m. Then we can write down the sum of 1 over g as the difference between two harmonic numbers, h m minus 1 minus h m minus n. We also sum minus g over g, which is minus 1. How many times? N minus 1 times. Rewriting this harmonic number as hm minus 1 over m, simplifying and combining with the case in which m is equal to n, we get that the expected value of the natural logarithm of determinant h Hermitian h is equal to minus small gamma, Euler-Mascheroni constant, times small n, the number of columns of matrix h, plus m, the number of rows, between brackets, the mth harmonic number minus 1. So this is 1/2 plus 1/3 all the way to 1 over m, minus m minus n times h m minus n minus 1. And this is 1 over 2 plus 1 over 3 all the way to 1 over m minus n, assuming m is strictly greater than n.